I am Ranjan Kumar, PhD student from NITRourkela, India. My supervisor is Professor Anand Pradhan, and I am going to present today my studies on globular clusters M3 and M13, where I have found extreme low mass white dwarf stars. So this study will be in ultraviolet band, and there we will find the hot extreme low mass white dwarf stars. And this study is a part of a globular cluster survey using UVIT telescope, and this is the second paper on that, and the first paper is of this sequence is and this is by Snehalata Sahu, and this is led by Snehalata Sahu, this global survey, and Annapurni Subramaniam, and this work has been done in collaboration with Professor Santik SC and Professor Devendra Kumar Ojha. So let me take you towards globular cluster M3 and M13. So M3 and M13 have peculiar in the sense that they have similar metallicity of -1.5 dex and age of around 12 giga-year. So they are thought to be perfect candidate of the second parameter problem of horizontal branch morphology in globular clusters, as we see that M3 has red horizontal branch and blue horizontal branch stars, whereas M13 has blue horizontal branch stars and extreme horizontal branch stars. And since they extreme horizontal branch stars do not undergo towards the thermal pulsations, they directly go to the white dwarf sequence from the as a AGB Menke phase or post early AGB phase. So they have a residual hydrogen larger than the normal white dwarfs in the atmosphere. So the cooling process of white dwarfs in M13 is slower than in M3, which has recently been proved by Chen et al. In 2021. So my observations are like we have observed with two ultraviolet filters like F148W, which has effective wavelength of 148 nanometer, and then the second filter which has the effective wavelength of 160 nanometer, and the bandwidths are 500 angstrom and 290 angstroms. So to complement the UV observations, we also have optical and near UV observations from Hubble Space Telescope Legacy Survey of Globular Clusters, which is publicly available and has been published in 2018 by Nardelli et al. And this HST observations are only for the inner region of the cluster, which is 3.5 arc minute cos 3.5 arc minute of at the cluster center. So we have we need to complement the outer region of the cluster with the other observations, which are the ground based observations, and this data is also publicly available by Stexon et al. 2019. So we have this 5 filters in outer region of the clusters UV VRI, and for inner region we have the precision photometry of HST observations of 275 nanometer, 336 nanometer, 438 nanometer, 606 nanometer, and 814 nanometer. So let me take you towards the images of the globular, how it looks. So if we see the optical one and the UV one, we can clearly identify that the UV one has a less number of sources, which are only hotter sources can be seen with the far UV images. So here we have plotted the optical color magnitude diagrams, where we the gray solids are the optical observations, and they are the cluster members, confirmed cluster members from the for outer region we have the Gaia cluster membership, and for the inner region we have the HST cluster membership. So on the top of it I have plotted the black solids, which are the UVIT observations in far UV band, and we can clearly see that only the horizontal branch stars and the white dwarfs can be observed in far UV filters. So similarly, if in M3, and here we as I said previously that M3 has red HB and blue HB, whereas M13 is populated with blue HB and extreme HB. We can color magnitude diagram of optical CMDs, we can clearly see that these are the extreme horizontal branch stars and the blue horizontal branch stars are populated in M13, and for M3 the red horizontal branch stars and the blue horizontal branch stars are populated. So let's talk about the UV optical color magnitude diagrams, where we have on the y-axis we have plotted the FUV filter F148W, which is far UV filter, and a color combination of far UV and optical, which is of at 148 nanometer and 606 nanometer. So we can clearly see that the horizontal branch is making a nice sequence here, but it is very populated. So we divided in 3 parts the horizontal branch stars, where we see that we call it for temperature ranges of 7.75 to 11.5 Kelvin, 1000 Kelvin as a blue horizontal branch stars, and 11.5 1000 Kelvin to 20,000 Kelvin as intermediate horizontal branch stars, and from 20,000 Kelvin to 30,000 Kelvin we call it as a extreme horizontal branch stars. And on top of the horizontal branch sequence, we see the brown diamonds, which are post horizontal branch stars, which have evolved from the horizontal branch phases, and they are burning helium in the atmosphere. So we see that in, around 31 post horizontal branch stars in M13, 27 white dwarfs. So these white dwarfs are like these are the black diamonds. These are the confirmed regions from the in UV optical CMDs, which have been probed in previously in Globals 1 paper, which is the UV81 paper, and then with Galactic and HST also. These regions are clearly probed as a white dwarf regions. So we found 27 white dwarfs in M13 and 29 white dwarfs in M3. So these are just probable members, which we will try to do further analysis and try to see that how they are matching or not as a horizontal branch. But here I would like to focus that we in M3 we see rarely very few EHB and IHB stars, like 4 in extreme horizontal branch and 4 to 5 in intermediate horizontal branch stars, and the post horizontal branch stars which are above the EHB and IHB region, they are very less, and so they we can say that the post AGB or AGB Mancue stars would be very less in M3 than in M13. So we see 3 post AGB stars, 29 white dwarfs in M3. So to further probe, we use the spectral energy distribution fitting for UVIT and HST filters for the inner region of the cluster, and UVIT and UVBRI filters for the outer region of the cluster, and we fitted with the Coester white dwarf model and Lavenhagen white dwarf models for to get their physical parameters like effective temperatures, luminosities, radius, and and using their T effective luminosity plots we determined, and cooling sequence we determined the masses. So I'll further discuss about the masses of the this white dwarfs. So we could fit only 48 white dwarfs out of 56 white dwarfs observed detected with M3 and M13 in UV bands. So in this, out of 48, we detected 24 white dwarfs in M3 and 24 white dwarfs in M13. So this the temperature ranges, we can see that for fitted white dwarfs we got as a 19,750 to 100,000 Kelvin for in M3 white dwarfs of M3, and for white dwarfs of M13 we got 90,750 to 60,000 Kelvin for of effective temperature, and the luminosities are in range of 0.17 to 2.0, and for in white dwarfs of M13 we get the luminosities of 0.23 to 2.8. Similarly, the radius is also very less, like 0.009 to 0.05 and 0.02 to 0.06. Here I would like to point out that we see that most of the M13 white dwarfs we see towards the towards little cooler than the M3 white dwarfs, and they have a little higher relatively higher luminosities than the M3 white dwarfs. Okay, let's see what are the cooling sequences we have used. So we have used a range of masses, cooling sequences of range of masses of white dwarfs, like extremely low mass white dwarf cooling sequences from Althos et al. 2013, which is in the mass range of 0.15 to 0.43. These are the helium core white dwarfs and has been generated using the in a binary sequence of neutron star and and 0 is main sequence star. And also we got the carbon core cooling sequences from the Renaudot 2010, which is in the range of 0.5 to 0.86. And for massive white dwarfs, we get the cooling sequences from Althos et al, which is 1.06 to 1.28. So the cooling sequences are plotted like the black one are for the low mass white dwarf cooling sequences, and the gray one as the high mass cooling sequences. So it's in increasing order from right to left. Okay, so we found 7 white dwarfs in M3 and 12 white dwarfs in M13, which are lying in between 0.18 to 0.43 solar mass cooling white dwarf cooling sequence. 15 are in between 0.43 to 0.50. 5 white dwarfs are in M3, which is lying bluer than the 0.86 solar mass, which is the long dash line. We see that the 3 are in between the 0.86 to 1.10, and the 2 are very far off from the white dwarf cooling sequences, which might be like field stars, or if they are white dwarf, I don't have any solution for that. So we have also plotted their mass ranges, like mass distributions. We can clearly see that the cooling sequences from the cooling sequences what masses we got are for M13 it is clustered near around 0.15 to 0.5, and for M3 it is distributed up to 1.1 solar mass. And there in their radial distribution from cluster center towards to the outer part of the clusters, we see that 80% of the white dwarfs of M3 are lying within the half-light radius of the cluster, and for M13 it is 58% of white dwarfs which is lying within the cluster region. So these are my conclusions. We find 24 probable white dwarfs in M3 and M13. SID fit suggests their masses as they are hotter from 19,000 Kelvin to 100,000 Kelvin, or in M3, and 19,750 to 60,000 Kelvin in M13. So a comparison with cooling sequences, we found that 19 white dwarfs are in the mass range of 0.18 to 0.43, 15 are in the range of 0.43 to 0.50, 6 are in the mass range of 0.5 to 0.86, and 3 are in the range of 0.86 to 1.10. So these results are in under review in MNRS. So thank you all, and I would like to take questions.
Very much. Yeah.
Thanks. Nice work. Sorry if I missed this, but what are the metallicities of the two clusters?
Minus 1.5 dex.
They are both same.
Similar. I mean
Okay.
1.5 and 1.53.
Okay. Thanks.
So I'm really interested in the masses that you derive. I mean, a 0.86 solar mass white dwarf
Yes.
evolved from perhaps a 1.5 solar mass star or 2 solar mass star or something along those lines. And those stars are long gone in these clusters. So how do we account for a 0.86 solar mass white dwarf?
So they might be in binaries, so that they stay longer in their phases. Since they are all in within the at the cluster core, so they should interacting in binaries.
So these would be different than, say, some other clusters for which deep Hubble data exists, yes, for which there's no evidence for white dwarfs this massive. So what's different here? Well, another question, maybe related. You don't have proper motions. Can you do a proper motion cleaning here or no?
No.
No. Okay.
Yes.
Thanks. Can you go to your last slide where you had the number in each mass bin?
This one?
The conclusion slide?
Okay.
Yeah, so it looks like about 80% or less than half a solar mass, right?
Yes.
So maybe a similar at least somewhat similar distribution to the Kilich et al. One that Ingrid told us about, where there are a lot of low mass white dwarfs. But these are metal pore clusters. So, do you have a sense of how much that's driven by them just being brighter and easier to observe? Or do you think if you correct for selection effects, it's a similar mass distribution to the metal-rich cluster?
Sorry, I did not got your last part of question.
Well, yeah, I'm just. Do you think this mass distribution is consistent with the one from NGC 6791? Yeah.
Okay.
The metal-rich one that Ingrid talked about.
Okay.
Here. Regarding those masses, I see that you used Renedo 2010 cooling. You use the whole sequence, or you use the coolings?
Coolings.
But, how do you compute the total age?
I did not talk about their age, so.
Just a comment. These are low metallicity clusters.
Yes.
So in those models, if you use the ages from those papers, those are solar. And lower metallicity stars tend to evolve faster, and also the progenitors tend to be lower masses. Okay. So maybe that 0.86 is actually lower because of metallicity. And the difference between solar and that metallicity that you show is going to be important.
Okay, but they are cooling sequences, so I mean, if you see there, so the luminosity won't change. If I mean the ages can be different, but the luminosity will be similar, right? For the cooling sequences.
No, depends, but no, there are differences. There is difference in the central composition that you're using. There's also difference in the amount of hydrogen that is left on top of the White Dwarf. The massive ones, the 1 point something, I don't think that could come from single cell evolution because they are gone. But that, I think you should check the metallicity dependence of the models that you're using to compute the cooling and the masses. Okay. Maybe that will change a little the masses.
Yeah,
Thank you.
It's not very much constant because you see the error bars are very large, so it's just a probable.
So I think we have time for just one more quick question, if there are any more. One more. If not, let's thank our speaker.
Thank you.
Thank you.